All right, yeah. Today we have Anna with us, and Anna will share her thoughts and her results, which she published very recently in a very good publication. Basically, you were interested in how different neurotransmitter systems have an interplay, and by that interplay, affect how we deal with complicated situations requiring cognitive control. Very interesting topic, I think. But what was the main motivation behind to start with that sort of research?
Yeah, to start with, I'm very fascinated by neurotransmitters in general, and because these are like these tiny little powerful messengers in our brain that help neurons to communicate not only with each other, but also transmit signals throughout the brain. So in our study, we essentially focused on two key groups, which are catecholamines, like dopamine and norepinephrine, and amino acid transmitters like GABA and glutamate. Yeah, we know that these to interact, and they are crucial for cognitive control.
But okay, why did you really choose these neurotransmitters? I mean, you could also have chosen different ones, but what's so fascinating about these two things?
That's right. I really want to emphasize that they are really crucial for cognitive control processes, which in essence enables us to have goal directed behavior and also control our thoughts and behaviors. So, despite previous evidence, it was still a little bit unclear, or rather unclear, how their interaction does really impact cognitive control. So in our study, we were really interested to find out how specifically the neurotransmitter GABA does influence our response to the ADHD medication methylphenidate, which does target the catecholaminergic system and its effect on behavior as well as electric brain activity.
I mean, this is really a fascinating question, but also a very challenging one, right? So it is not that you could easily pharmacological modulate both of these neurotransmitter systems at once. So you have to find another way around. Okay, one could be by pharmacology and maybe some other method. So how did you really tackle that gap in our knowledge? What did you do?
What we did in essence is we used MR spectroscopy as well as EEG to find out how methylphenidate does actually impact or affect brain activity patterns.
Okay.
And we specifically focused on theta brain waves, which can be used or which, yeah, are a measure of interference control, which in essence is our brain's ability to filter out distractions and focus on the task at hand.
All right, so I mean, there are many different studies on theta band activity out there, stressing the importance to, let's say, integrate perception and action. Especially medial frontal theta band activity is thought to be, yeah, important for cognitive control processes in sort of a surprise signal monitoring function. Okay, these all taps into dopaminergic processes. That's true. But how do you really accomplish this modulation by a pharmacological process to see then at the level of theta band activity, and how far does this affect really the behavioral level?
Okay, so for this, we started off with the MR spectroscopy measurement, which is in essence non-invasive method that uses magnetic fields to measure GABA levels in this case. And now comes the important part of having two EEG sessions, on which one of them the participant received the methylphenidate, the ADHD drug, and the other one the placebo. So yeah, to answer your question, we did in essence find out that actually the theta brainwaves were increased no matter if the participant did take the drug or had task experience. So the theta brainwaves were increased whenever the mental effort needed to perform well was high.
All right, so what you basically say is that your pharmacological intervention is dependent on many different factors, which is in some sense the GABAergic system, but also the cognitive effort that needs to be exerted. And only if there is a high level of such necessary, it actually makes a difference, which is fascinating because people would normally think it would act nevertheless. The cognitive affordances are high or low, right? But you show that it is not that easy. But I'm wondering, for this to show, how do you integrate the knowledge that you have from your GABA spectroscopy data with your pharmacological and EEG data?
Yeah, now comes the important part. So, to really make the most out of this information we collected from the MR spectroscopy, we used the GABA, the neurotransmitter GABA, because we want to find out how it does relate to brain activity patterns and whether it can maybe even predict it.
Mm-hmm.
So, instead of going for traditional methods, in our study, we went for machine learning techniques. But instead of really going into the complex details of this method, let's break it down a little
Okay.
bit.
Yeah.
So, one has to imagine GABA levels as sort of clues that we did fed into this computer model, which is like a brain-inspired artificial intelligence. And this model then somewhat figured out how these clues, which is the GABA levels, do connect to the brain activity patterns, which were the theta brainwaves.
And through this analysis, you then figured, okay, that the GABAergic parameter that you fed into this neural network model was especially then predictive when there are high cognitive loads or lots of efforts to be exerted in the task, and when you have, let's say, taken MPH, or?
Yes, correct. To give an example, especially the region called anterior cingulate cortex, where we measure GABA from, seems to be a very good example or be very important in this case, especially when the mental effort needed to perform well was high.
All right, so wow, I mean, then you have a specificity regarding the brain region that's important, a specificity regarding the neurotransmitter, which is GABA, and or the catecholaminergic system, and for example, the role of the level of cognitive effort that needs to be invested. So kind of an intricate balance that is there. But I would think that this has really strong implications because, I mean, MPH is a first line treatment, for example, in ADHD. I mean, you have not been addressing ADHD in your study, but nevertheless, I would think that there are strong implications for that.
Yeah, for sure, I would definitely agree. So our study somehow dives into the complex interplay between drug effects, brain chemistry, and cognitive performance. And as you already did mention, methylphenidate unfortunately is not a one-fits-all drug, meaning that there's many factors that play into how effective it is for one individual. And our study definitely shows that it's brain chemistry, task complexity, and maybe even several other factors that should be counted in. So yeah, moving forward, hopefully we can move to a new chapter talking maybe into the directions of individualized medicine, saying that, okay, we use the insights of this study to really improve and personalize medical treatments for the patients, and saying that we are tailoring the treatment based on the patient's unique brain chemistry and also the tasks that they need to tackle. That would be, yeah, a hope for the future.
Oh, that's fascinating. I mean, this is really, really fascinating outlook. I mean, there are many different steps to go into that direction, but I'm sure that you will do. Will be fascinating to see that in the future. Yeah, thank you very much for sharing your very interesting and also relevant research. Thank you for being with us, and thank you very much for watching us. Take care and goodbye.